Okay, so as we had planned, we'll be talking about an important topic, and that is called relaxation in NMR. So this is so we'll be talking about this. I'll be giving you as we are into the quantum background of portion that we are dealing with. This sixth lecture is actually for quantum background of NMR, not exactly NMR spectrum. That is something that we'll be spending months in coming. So I'll be giving a little bit about that as well, and then finally I'll talk about how this relaxation parameters are measured in NMR, and what do they really tell you, in which situation you can actually measure them in your research work when they are going to be useful. But to start with, let me tell you a common misconception that has been created by a wrong picture in many NMR books, many NMR text available over the internet. I have seen it many times. And then this particular myth, this particular wrong conception, first, let me remove that before I put back the correct information to you. So if you remember, I have drawn previously a situation like this. So we had this B0 field. This is my B0 field. This can be the Z direction. And then the two cones that were created. One is the cone with this all the spins over here, and then they were all in the alpha state, which is aligned. And then we had another one which is down over here. So this line should be a little longer like this. And then we had another cone which is all the spins in the beta state. That is something that we had created previously, correct? Something we have already done. I'm just reminding you again, beta state. And we know that this state has maybe say n alpha number of spins or n alpha number of molecules that is going into the alpha state. This might be having some n beta number of states. And then we know that n alpha is going to be slightly greater than n beta. And that is how we get, which we always drawn a small, tiny bulk magnetization. We often call it M or M naught. Correct? This is fine. And also we had seen that, well, this particular thing is not rotating, so we had to tilt it out of the Z line. And for that, we had to apply some RF field, radio frequency, and that will create, in turn, that will create this nice small magnet going from Z direction to maybe the XY plane, correct? And then this will start rotating, and then it will be observed. Fine. All these things have been done. Now the question is that we know that this particular state that spins in either alpha state or this beta state in quantum mechanical way, we saw these are called eigenstates of this MZ. So they would like to be there, right? That is basically a stable situation there in alpha state. And therefore, this particular situation that we have a tiny bulk magneting along the Z direction, that is also equilibrium state. If you leave this sample inside the NMR spectrometer for long time, 1 hour, 2 hour, 2 days, 3 days, it is always going to be nicely over there. The M naught will not precess, it will just sit there. Now, once I have to give this RF pulse, I'm just creating from this particular situation to this particular situation. Here, this one is created, which is tilted on the XY plane, is not an equilibrium situation. So therefore, as nature always does, because we have given this RF pulse, so I have actually pumped some energy to the system to create this particular non-equilibrium situation, the nature always will release that extra energy somehow, and then it will go back from this particular state to back to the equilibrium state like this, correct? This process of going this particular situation where I have some X or Y magnetization, some detectable bulk magnetization, from this particular state going back to the original equilibrium state where I have only the Z magnetization, nothing is available, this process is called relaxation. So the thing is that this particular process which goes from here to here, correct? This is basically your relaxation. It is relaxing back to the equilibrium. That's how it is called, relaxation. Okay. Now the question is, now comes the misconception. So misconception says that, well, it is drawn in this way. This is the axis. And people say that, well, let me start from this particular blue one is now my magnetization, which is in the XY plane, correct? I started it because I have basically, I started this from here. I started from this Z component here, correct? But then I have flipped this over here like this using an RF pulse. So I have started my journey from this XY plane. Fine. Now, as it is moving, it is basically moving because there's a Larmor frequency is going on. That is what we are observing. At the same time, it is relaxing back. So people that tend to give a picture like this, and you'll see this picture many times. So they give a picture like this is moving, and then it is coming out of this, and then is going back and going back and going back to Z direction. So this particular picture, that as if this particular XY plane, I hope you can see my pencil, right? So this is there, and then it is rotating at the same time. It is rotating at the same time. It is going up. So as if it is rotating, and it is like a spring. It is going up like a coil. It is going up like it is. This picture is wrong. And I can prove this. This picture is wrong. I can prove this. How? If this picture had to be correct, then I can understand from simple logic that the time it will take to vanish this X component, because it is slowly going up, no? So the time it will reach from here to all the way to here, the time it will take this X component to vanish, that exact time it will take the Z component to appear, because it is starting from X, and with rotation it is going to the Z. So if this whole process going from the XY plane rotating into the Z, it takes about say 2 milliseconds, then after 2 milliseconds the entire Z component should come back and entire X or Y component should be vanishing, correct? So therefore the amount of time taken to X and Y component to vanish and then Z component to reappear should be equal. But you will always see that that is not the thing. So that is why we have two different time constant we'll be talking about. One is called T1, another is called T2. I don't know if you have heard about them. You will be hearing them a lot of time in this NMR course. This time constant tells the typical time constant it takes to Z component to build up. Coming back to this, so coming back to the Z component to build up. And this time T2 is the typical time constant, typical time it takes to this X component to or Y component to vanish. Now question is, if this is the picture, then T1 and T2 should be same. In fact, not Y comparable. They should be exactly the same. Correct? They should be exactly the same, but they are not. For example, if you take a protein, correct, your T1 might be of the order of 4 or 5 seconds, whereas your T2 will be something order of 20 milliseconds, maybe well less. That is a big difference. So that means that is what is happening is that not a single event, but there are two different events are going on. So two different events. One is the event of T1 or the Z magnetization buildup. Another is the XY magnetization getting vanished. So these two, we have to understand, these two are basically the relaxation chapter. If you understand these two processes, you understand what do you mean by relaxation and NMR. So two different processes going on. What are those? So we had written down or drawn like this previously, that I have a state and then I create another one like this. Right? So now if we just imagine that we have number of spins there, correct, we will find that maybe we have a little more onto this lower energy state, which is called the alpha state, than the top one. Or I can, okay, fine, the top one. So this beta state is slightly less in number, obviously n beta is lower than this alpha state, which is the lower energy, and that is the thing. So when we apply this RF pulse, the first thing that happens is that we actually create or disturb this nice equilibrium arrangement of population. So this arrangement came from Boltzmann distribution. Given a particular delta E, given a particular temperature of the sample, we know that the distribution, even two states, are given a Boltzmann distribution. This Boltzmann distribution is first thing first. This Boltzmann distribution is getting disturbed. So what happens is that first we create an equal population. I'll be giving a little bit of math behind this, so then you'll understand in a quick way I'll be doing. So this first thing that is happening is that one is that readjustment of population. Now suppose you have created exactly the thing is that we have exactly equal number of population being created. So what you have done is that some few of these are removed here, and you have just taken them up, correct? You have just something like this. Okay, exactly 4 and 4. So what happens is that if I just do this, that means there are a few are going from, as we are giving energy, few are going from alpha to beta. Actually, it is not only alpha to beta, it alpha to beta, beta alpha, both happens, and then it goes to a situation that actually has this same equilibrium, the same population. So now what happens is that if I have created a situation like this, that the alpha state and the beta state exactly have the same number of spin, the n alpha is exactly equal to n beta, then this will vanish, correct? There is no difference, so therefore z component will vanish. So therefore the z component will vanish just because we have created an exactly equal population. And then, but that doesn't make any x and y component, because what I have told before, these spins which are rotating or precessing in this particular cone, right, they are all over this plane. So therefore the xy component that we have created previously, they're all spread. So if you just look at this xy component over here like this, they'll be seen like this, that they are every direction. The xy plane will look like this. Right. So even if I make a situation that I have now exactly n alpha is equal to n beta, which will happen, xy component will still be not creating. So therefore we understand the process one, which is the readjustment of population, only can take out the z component out. That means z component is vanishing, but that doesn't mean that immediately the xy component is getting created. In order to create the xy component, we have to have something else, and that is called creation of phase coherence. This whole concept of phase coherence is very mathematical and quantum mechanical, which I'll try to avoid. I'll just try to give you some idea about with pictures and maybe a little bit of math at the end. But the thing is that, what do you mean by phase coherence? The phase coherence is that imagine that now the xy plane is actually not looking like this. Just by giving this RF pulse, we have created a situation that those which are having, so basically those which were in alpha state, they are kind of bunch into one direction, and those in the beta state, they are bunch into the different directions. So what happens is that a picture is coming like this. So the xy and now the xy plane will look like so this will be your n alpha number thing, and then this is going to be n beta. So therefore, what they are doing is that they are still rotating into this cone, but now they're not rotating exactly all 365, but they're rotating, actually they're all bunched in this one direction. That is the best picture I can give you for this quantum mechanics. It is a classical picture for quantum mechanical thing, which is not really allowed, but still I can give. So then what happens is that I have a situation that in this x direction, right, I have a relative component, which is this direction, because they are now bunched, right? But I have another component. I have another component in this direction, right? But as this is an alpha number of thing and this is n beta number of thing, again the same thing happens, that we have a tiny amount of, I have a tiny amount of x component. So this is your mx that is going to be created because of this bunching. So this is called, this particular process is called a phase coherence. That means earlier the phase means that in which place it is resting was completely decoherent. That means one spin is in 0 degree, another spin 30 degree, another spin 15 degree, is all over the world. So therefore this is no coherence. It was absolutely decoherent state. But now they are not like this. So their phases are either bunched towards 0 or they're bunched towards 180. That means the phase of one spin is correlated to another spin. They're having similar values. This is called phase coherence. That is why often you will see that even in the lectures also or book also, the x and y component of magnetization in NMR is also called coherence. Like for example, you might learn this term later on, coherence transfer, correct? I'm not going to those details, but coherence transfer. So what do you mean by coherence? Coherence is actually basically this. I'm trying to give you a picture out of this quantum mechanics, but this is what phase coherence is. Now, once you have this phase coherence, what happens is you have gotten mx, this particular term, but the z component is entirely because of the population difference. Now the thing is that there are two processes will go simultaneously. First, this phase coherence that you have created will slowly get disturbed. Like for example, all the spins, they were rotating in the same phase, all 0. Slowly they will interchange energy between them, and then slowly it will basically slowly fan out like this, correct? And then after some time you say that, well, it is not exactly bunched like this, but rather they are basically a little more disturbed like this, but still there is something is there on, and the black one is also maybe disturbed like this. After some time you'll see that these red ones are absolutely have started going back again to this absolutely decoherent state, and then the xy component is out. So therefore this process, that going from a very coherent phase situation to absolutely decoherent phase in the xy plane, this a component, that is, this particular thing is done in the time scale of t2. This is called the time scale of t2. It's an exponential process. I'll give you a little bit of the math, but this is called the t2, and this is called also a transverse relaxation. Transverse relaxation, because this transverse component that is coming off the phase coherence is getting destroyed. So this phase coherence becomes decoherent. That is one thing. But this process, what happens is that even when you have this process takes generally much longer time, particularly for large molecule like proteins or something. It takes a much larger thing. So what happens that in this particular case, the spin system has to deliver this extra energy that has originally pumped in by this RF. This particular energy had to be given to the lattice. What do you mean by lattice? Lattice means anything which is available in the quantum mechanical scale to take up this extra energy, so that this energy, this particular which we pumped into the higher energy, they can come down and then actually get restored this equilibrium population difference. Then N alpha is slightly more, N beta slightly less, and all those things. But for that, this energy has to come out from the spin system to the lattice. Lattice is anything other than the spin system. It can be vibrational states in the molecule, it can be rotational states of the molecule, it can be anything. The only thing is that this energy, which is a very tiny amount of energy, because I have told you previously, delta E is extremely small, this extremely small amount of energy had to be taken out, and then these extra ones which are in the beta, they will come down. And then again, when there will happen this particular in alpha and beta, this particular condition will be getting restored, and then this Z component will slowly coming up. So killing of XY component, that is because of decoherence, and gaining of Z component by readjusting the Boltzmann distribution again, these two are completely different phenomena, completely different thing. They are happening simultaneously though, and that is creating this this particular thing. That is why this one is called a T1, because this is called a spin. This is called spin lattice relaxation, because the spin system is giving extra energy to the lattice relaxation, and this time constant called T1. So basically it's an exponential thing, process. I'll tell you, this is T1. So this particular thing, in general, for large molecule, T1 is much longer than T2. So that means this process of this adjustment is much slower than the decoherence creating. The decoherence can be, this process of coherence to decoherence will be coming in few milliseconds. However, it will take several seconds to readjust this particular population difference. So these two are completely different things. Now the question is that where from this particular picture got originated? Why this particular? Because if there has to be some source that this particular picture is now taken in many books, this spiral thing. If I plot the T1 and T2, I plot T1 in red and I plot T2 in blue. If I plot it as a function of omega tau c. What is omega tau c? Omega 0 tau c. So omega 0 is the Larmor frequency. If it is a proton, then Larmor frequency of whatever 4 megahertz in the spectrometer. And tau c is the rotational correlation time, kind of a time, roughly, not exactly, roughly a time a molecule takes to rotate by, say, there are different ways of defining it. Somebody tells that it takes a time to rotate by 180 degrees. Somebody said it is by 1 radian. But nonetheless, basically tau c correlation, rotational correlation time is that how fast the molecule is rotating in solution, correct? That is basically a time constant of rotation. So this product, omega tau c, values of this product can be plotted. And if I just plot this, what happens is that, let me just tell you. So red I have taken for T1. The T1 looks something like this. That is the T1 curve. As the omega tau c is increasing, it is the T1 first drops and then starts increasing again. Whereas the T2 is something like this. So it is basically going very slow like this. So that means the T2 that starts dropping and keep dropping and keep dropping and keep dropping as the omega tau c is increasing. Now question is that what do you mean by omega tau c increasing? So in a particular spectrometer, omega 0 is fixed. The Larmor frequency of proton, suppose it is fixed, 400 megahertz or 700 megahertz, whatever megahertz spectrometer you're using, it is fixed. Then omega tau c is increasing simply means tau c is increasing because omega 0 is already fixed. Tau c increasing means it takes on an average longer time the molecule to rotate by one full rotation, suppose, if we define in that way. When that will happen? When this molecule is pretty big. If the big molecules rotate much slower into the solution rather than the small molecule which rotate very fast. So therefore, omega tau c is going to be very large given a particular omega when the tau c is very large, very long. Now this particular tau c is long when the molecule is very large. So therefore this particular region, this is basically big molecule. Molecule. And this is basically small. So when you have small molecules, then omega tau is small, but in the large molecules, then this is the thing. Now you look at this, where this misconception came. For the large molecule, like for example, a protein or something, I have a very large T1, right? Very long T1. That means it takes a very long time to readjust those levels, the Zeeman levels. However, the T2 is almost zero, is very small. That means the decoherence is done pretty fast, very quickly it is done. But for small molecule, you can see that T1 is actually equal to T2. The time it takes for this readjustment of T1 is almost the same time it takes for the decoherence to get to kick in. So therefore, if I have a scenario for all small molecules, because NMR was discovered with small molecules first, proteins and RNAs or DNAs we are doing just now when we have 700, 800 megahertz, 1 gigahertz megahertz. But when NMR started historically, that time only small molecules people used to do. And when they measured T1 and T2, when T1 and T2 was discovered, they always found that for the small molecules, T1 is exactly equal to T2. So therefore, if you really now go back, if really you have T1 is equal to T2, which I was talking about that time, you actually get this particular thing, although wrongly, but you will be still getting this particular picture that the time it takes the XY component to zero, to make a zero, is the exact time it takes to Z component to build up. And this particular wrong picture came because we had initially T1 equal to T2 for the small molecules. And that is how this particular thing is. Okay, fine. So we have, this is basically the idea that we have got. Now let me talk about quickly how this T1 and T2 are actually measured in experimentally. So as I have not taught you pulse sequence and all those things, so I'll not be giving you much of detail of pulse sequencing, but logic I can tell you the logic, the how this particular thing is being created. So the idea is, what I'm going to do is that, let me start from the T1 measurement. So T1 experiment. If you have any question, you can always ask. If you have anything, any doubt, whatever you have done, you can even definitely ask. It is also called inversion recovery experiment. This name of this T1 experiment, the experiment with which T1 is measured, is called inversion recovery experiment. What do you mean by inversion recovery? Let me draw this thing again. And then we had, oops. Okay, so we had less number of things, and therefore what we had a situation like this, we had a Z component, correct? So we had a simple a beautiful Z component, right? This is the situation. This is the beta state. So there in the picture, the alignment aligned, the lower state is actually drawn in the top because it is aligned to the magnetic field, and that is the lower energy. So we have a Z component. Now, if I just do a single pulse, which we already have understood, a single 90-degree pulse, what will happen is that this will be created a small magnetization, correct? Like in X direction, suppose. And now if this X direction is, suppose, is giving me a nice NMR peak, suppose. Somehow it is giving a Fourier transform or whatever it is. Now, what happens is that I'll be doing, so therefore, what I have understood is that the rotation that has been done, that rotation is kind of this type of rotation. That is why it has reached from here to here. Right? I have drawn this way in positive X direction. Now, suppose I do something that this particular population difference is inverted. That means these many are coming up and these many are coming down. So I can, let me try giving this into a different color so that, okay. So then what happened is that I'm doing something so that, let me copy this so that I don't have to draw again. Perfect. Now I have done a inversion. So this inversion is done by using a pi pulse, pi or 180, we call it a 180-degree pulse. If you ever have time or interest in knowing about what do you mean by pi pulse and 180 pulse, how they work, a little more into NMR theory, well, you can talk to me, you can talk to anyone, you can read. But nonetheless, if I use a pi pulse, what happens is that they get flipped. So therefore, I can think this way. It is not exactly true that these 3 will come down and this 5 will, but actually the number wise will be having, that is why I was actually not using a different color, but now that's fine. something like this, correct? We have this is, so this color coded actually give you the wrong idea, that as if these five molecules have gone up. Not like that. They always go back and forth, but on an average this number is maintained equilibrium. If you have n alpha and n beta and beta, that doesn't mean that they're fixed log. They always keep going, because you have a thermal agitation, you have temperature in your sample, they keep doing. But on an average, that is the ratio they maintain, the Boltzmann distribution they maintain. But now if I have this, then what happens is that I can draw this whole thing is going to be like this, correct? Now we have flipped it, so therefore this original Z magnetization, tiny one m, that has become minus m. So therefore if this was m, I can call this as minus m, correct? And then what happens that if I now directly put a 90 degree, if I just put a 90 degree here, the same 90 degree, then as it has flipped, correct, and it is the rotation is happening clockwise, so from here it was coming to this, but from here it will go to minus x. So I'll get something like this particular thing, right? And that will give you, and a minus x particular thing will give me a peak which is inverted, because it is, if everything is same, just before the experiment I give a 180 degree pulse, then it will invert the thing and then it will minus x. But then it is a starting point. What happens is that I have to see that in what time scale this particular, now we have disturbed it, correct? This was equilibrium, but now I have changed this. This is not equilibrium. So an equilibrium is that again this it will be 3 here and 5 here, correct? That is the equilibrium distribution. So what I'll do is that I have done this particular 180 degree, then I wait for some time. So my idea is that I'll give a 180 degree and then I wait for some delta time, then I give this 90 degree, correct? So 180 degree, then delta, there's a kind of delay, then 90 degree. Then what happens is that this particular redistribution of population will start happening immediately after I give this 180 degree, because that's non-equilibrium situation. T1 will kick in. So at some point of time, what happens is that maybe the situation is something like this. So one has gone down, and then one has gone up, something like this. Something like this. So that means here it is just now it was inverted, now it has 0, and then it will go to the positive one, correct? So therefore if I just now change, just keep doing this, and then this after 90 degree like experiment done, correct? So this peak is coming. So how did it look like as a function of delta? Immediately, to start with, it was 9 like this. So let me just draw one line so that you will understand. So this was the peak. Then after delta a little bit, the peak will be smaller because a little bit of readjustment is done. Then this is going to be even smaller. Then it is going to be even smaller. Then it will be 0. That means when it is exactly equal, and then it will start free because relaxation is happening. Then it is going to be like small, like this, and like this. Correct? So if I just plot it, correct? If I just plot this particular thing, this tip, this particular thing, I'll get a situation like this, that it is going to be starting from, this is 0, so starting from -1, because this particular thing is -1, and it will go all the way to 1, and then this it is not going to be a linear, it's going to be something like this. So this particular tip is going to go from -1 to +1, because -1 is inverted, +1 is proper, it will go through the 0, and this particular thing, and this particular one is going to be some the equation is going to be an exponential one factor with T1 being the rate constant. Right? I'll give you the equation at the end, but this is going to be the rate constant. So this is how inversion requires. So this, what it means is that first I invert it, correct? That is why first I invert it, then I allow it to recover. That's why it is called inversion recovery experiment. Inversion recovery experiment. So I first invert it. Invert means invert the population, and then I'm giving it time to recover it to the coming back to the Boltzmann distribution. And in each time, so this is done, actually each one has to be done separately, separate experiment. So 180 degree, some delta 90 experiment, okay, fine. Again you come back proper, again you start from 180 degree, a slightly longer delta, and then 90-degree thing, and then you go from starting from absolutely 1 millisecond delta to all the way to 5 seconds delta, and you get a nice the point. So that these points which are coming over here, this point and this point and this point, they will be sitting just on top of the point like this point and this point and this point. And after some time, they'll just simply flatten out, correct? And exponentially, they'll reaching this particular thing. So this is called inversion recovery. This is how T1 is measured. How the T2 is measured? Well, T2 measurement is conceptually much easier. However, there is one single problem which I have to tell you. So how it is being done? So the idea is that I have created this particular situation that this. So I have this X component, correct? This X component is, I have to now simply find out that how this X component is rotating with some omega 0 Larmor frequency, correct? But at the same time, this X component is going down, right? This particular thing is going down. So the idea is that you might simply say that, you do not have to do anything. You just observe this signal, and if you just this signal is observed, how this particular thing will look like. It will start from a maximum value, and then it will start oscillating, but it will oscillate, and progressively it will become smaller in intensity because it is relaxing, and then it will be zero at some time, correct? So therefore, you simply take this particular curve. It's not a big deal. You just take this curve, and then this is this particular thing you are measure, and this is going to be your T2 curve, correct? This is going to be an exponential decay, and that is your T2 curve. Fantastic. For measuring T2 is pretty simple. You just simply have to have this thing. But by the way, one particular thing, the signal actually looks like this, and this signal is called FID in NMR. This is basically this is free. Free means it is free from any perturbation. That, like, we have already given the RF pulse, and then I have switched off the RF pulse, and then this is rotating. So this is free of any perturbation, free induction. Because I told you that how it is measured. It is measured because this bulk magnetization is rotating, and you have kept a solenoid, and this tiny magnet is inducing an EMF, because you know that in the vicinity of a solenoid, or vicinity of a coil, if a magnet moves, then it induces an EMF. That is why induction. Free, because it is free of any perturbation or pulse. Induction and decay. Why decay? Because relaxation is happening. Decay, I can see that decay is happening. Relaxation will happen. So this is decay. So that is why an NMR signal is called free induction decay. Free from pulsing, induction because of the process, decay because of relaxation. Anyway, that's a side remark, FID. But this is not the way you can actually do it. You know why? That's because this T2 that if you measure, this T2 is not actually the true T2 that is happening inside this particular spin system. The spin system is dephasing, this decoherence is coming in a particular T2, agreed. But that particular T2 is not the one if you measure directly. This particular T2 is called T2 star. This is slightly shorter than the original T2. That's because you have the sample. Correct? So you have this particular sample, and you have this B naught, correct? Now the question is that if what happens is that suppose there is no relaxation, absolutely zero relaxation, forget about relaxation. So then the spin that is at this particular bottom, and the spin which is basically having on the top, they are having Larmor frequency given by omega 0. Gamma is same, all protons, B0, because B0 is the magnetic field of the spectrometer, 1 minus sigma, some sigma, maybe a particular methyl proton you are talking about, or a particular aromatic proton you are talking about. The sigma is same. Sigma will differ from one type of proton to another type of proton, but I'm taking the same type of proton in different molecules spread over the entire sample. And then this is going to be the omega 0, correct? But the thing is that in magnetic field, this field is not really homogeneous. The field is, it is not possible to create an absolutely perfect same Tesla everywhere in the sample, because it is extremely high Tesla, 10 Tesla, 16 Tesla magnetic field, which is huge. I have already given you in the second class what is the average size of an Tesla in a magnetic field in an NMR spectrometer. Like a 400 megahertz spectrometer has almost 10 Tesla. It is just engineering wise impossible to give you exactly the same B0 or the entire thing. So the B0 will change slightly. So if the B0 is slightly changing from one point to another point, suppose the B0 has a little bit of a slope. So on top of the B0, on top of the original B0, it is slightly more here. It is slightly more here and slightly less here. Okay, so what happens is that then the omega 0, which is the precision frequency, is slowly changing as these molecules are, which are on at the bottom of the sample tube, and the molecules which are on the top of the sample tube. As a result, if they are having slightly different B0, they have a slightly different omega 0, correct? So therefore, even if I start this particular situation that I am starting from all this, them are bunched up like this, so all these spins are suppose bunched up like this, correct? Absolutely zero, perfect, right? We have created a beautiful coherence. We have created all bunched up x. But then as they're moving, omega 0 and omega 0 is changing from a different thing. After some time, what will happen is that this one is just a minute, use red for a little bit of debunching will happen. They are not going to go in exactly the same direction. So by the time they come back in one more time, they have slightly dephased just because of this inhomogeneity. After another round, so this is happening just after one round. So it is started from a bunch, they go all the way, come back, and then a little bit of disturb because they are having different omega 0. Another round they come back, and then there will be more, and therefore what happens is that X component, which is basically in this direction, correct? The X component, which is the projection of all these ones, there's this projection is going to vectorial addition, correct? Here here you had a lot of, all of them has the same thing, but here they're only a little bit of less, so therefore the X component will go down. It will look like as if they are the signal decay has started, although there is no actual relaxation happening. So this particular extra amount of kind of relaxations, kind of a pseudo relaxation is happening because we have inhomogeneity inside the magnetic field, and that is always there. So for that, what happened to do is that we use a particular sequence called CPMG. This is a Karpusel, Mabel, Goom. There are four different people, four different scientists together in a paper. They gave this particular thing, or maybe Spinico, this to start with. Okay, that says that, well, all you have to do is that you have to start with a 90-degree pulse. So this is 90-degree pulse that is creating this XY plane, this bunch, nice bunch. Then you just do not start observing. If you just start observing, it will decay, but it will decay for both reasons. One is the original T2, which is the relaxation, and then this inhomogeneity. But we have to take out this inhomogeneity part out, correct? So what you have to do is that we have to simply take out the effect of this. So for that, what you have to do is that you have to create something called a spin-echo sequence. What is a spin-echo sequence? Spin-echo sequence is a delta, some amount of delta, then you have a 180-degree pulse, and then you have another delta. Then here you start recording, correct? You check the line length, correct? And then you change this particular delta, and this 180-degree this particular thing is there. So what happens is that why this particular thing is necessary. Imagine you have now you imagine this only two spins which have slightly different speed. So let me draw this. So this let me draw this. So I have this one, and now imagine I have just two spins. I have drawn several bunch here. You will not understand this. Suppose there's two spin and they have slightly different speed, because maybe one spin is exactly from the bottom of the pile, another is exactly in the top, so they have quite a bit of difference. So after one particular little time, what happens is they start from here. So they both start from here. They both start from here, correct? But after some time, what happens is that this goes to, oops, this comes here and this goes here, because they have a slightly different speed. So in some time they have reached here. Then after, this is basically the delta time. So after delta time, after exactly delta time, they have reached here. Now I have given 180-degree pulse. What 180-degree pulse will do is that they will reflect this whole thing about this line. This is basically will happen. So after the 180-degree pulse, we'll have a situation like this. So the blue and the red, blue will come here, and the black will come here. The idea is that you can clearly see that here it was the black, so black will reflect back here, correct? It will be down, and then the blue will be reflected back here. So there is a blue will be on the top and the black will be at the bottom. So that has been created, and then we'll be waiting another just tau delta time. You're waiting another delta time, and this delta time, what will happen is that these two will be coming close. So earlier in this particular delta time, it has reached only this much, but the blue was faster, so it reached this much. But then in this delta time, the same amount will come back to here, and this will be slower, so it will come back. So after delta time, they both will be coming back to here, correct? So then after delta time, what happens is that I can see that this is going to be, they're coming back here, because the thing is that big this way, but they'll not be coming back exactly there. They'll be slightly smaller because of relaxation of 2 delta, and therefore they'll be bunched again. However, they'll be smaller. So therefore, what happens is that we started from here. Now we started from here. This particular effect was happening because of the inhomogeneity. This inhomogeneity is cancelled out because of this particular pulse. It has come back. So therefore, this faster one came here, and then this coming back. The slower one came here and then come back, and then they bunched again. But this time from here to here, the 2 tau time has come. So 1 tau is here, another tau is here, 2 tau come. So then this has shortened. So now what will happen is that if this particular thing is positive, this is going to be a negative one, because earlier it was this side and now this side, but it is going to be slightly shorter. But if you just skip this, you put another 2 tau, another tau 180 tau, that means you have tau 180 tau, again tau 180 tau, then this will come back to here, and then it is going to be in the same side of the signal, but it is going to be much shorter. Again, they're bunched together, but they're shorter. Now imagine you have many of them, and then this particular thing will happen. All of them are fanning out, then basically flipped, and then again coming back. So therefore, they're basically they started from here. Then after delta time, they are fanning out. Then 180-degree given, and then they're coming back again. Again, they're fanning out. Then 180-degree given, then again coming back again. But each time they're coming back after the T2, because the T2 relaxation is going on. T2 relaxation I cannot cancel. That is spin interaction is happening. That is out of my hand. So therefore, what happens is that if I, after every time, if I just try measuring, after every 4 tau time, if I try measuring the signal will then now look like it has started from here, then it is going to be like this, then it's going to be like this, like this, like this, like this. So this particular, if I now take this point, and then if I plotted this particular thing, this will give me the exact T2 and not T2 star, because I have already taken with this spin echo, this particular effect, inhomogeneity effect is out. So that is basically called a spin echo sequence, and it's a very famous sequence, spin-echo sequence. Spin-echo sequence can be used for some other reasons as well later on, if you study something called HSQC, etc. There, inept transfer, coherence transfer. So spin-echo has a lot of thing. But the basic idea of spin-echo is that you get T2 instead of T2 star, which is basically, you see that if you just look at the FID, the decay of FID is T2 star. But this particular thing. Now the question is that that's one comment. I'll not got much thing is that the idea is that this particular spin-echo will work if it is assumed that during this delta time and during this delta time, this molecule which was sitting at the bottom of the sample tube is still sitting in the bottom of the sample tube here, because with the speed at which it is dephasing, at the same speed, the speed at which it is dephasing during the first delta time is the same speed with that it has to rephase during the second delta time. If by this time this particular molecule has gone from this particular point and diffused, suppose it has a diffusion has started. So this molecule during the first delta time was here, but during the second delta time it has diffused to this particular place, because obviously inside the molecules are not fixed there. They are going up and down, correct? So they are diffused. Then what happens is that during the time in which they were dephasing, speed was different, and the rephasing speed was different. So in one speed you went to the market, and if you are different speed you are coming back, then the same time you will not reach home, correct? That's the same thing. So that is why CPMG sequence, which is there, you say that don't take on single like don't take such a large delta and then 180 degree and another large delta. Then during that time diffusion will happen. Instead you take a series of very small delta, 180 delta, 180 delta, 180 delta. So basically this particular sequence, the delta has to be smaller, and then this whole thing has to be repeated several times. That is called CPMG sequence. Just an extra added on top of spin-echo. But still, CPMG sequence also has spin-echo as the central unit. Several spin-echos are getting one after one, so that the effect of diffusion doesn't come. Anyway, this time is already there, so I do not really want to go into any more math or anything. I hope at least I have given a flavor of relaxation, how they're measured, and how this particular thing is that. But just one last two sentences I'll take that where the T1 and T2s are useful, and that is basically you can come back to this picture. This particular picture, this picture is very important, because suppose I have a situation, I have a large protein molecule like this, correct? And then I have a small molecule which is a drug molecule, fine. Now this drug molecule is supposed to be attached to this large protein molecule. So what happens is that once it is free, this molecule is rotating very fast. Tau c is very small, correct? It will have a different values of T1 and T2. But once it is attached to the molecule as a drug molecule, the target molecule it has attached, the drug has attached to the protein, it will start rotating with this big molecule, which is rotating very slow. It is not rotating fast. So therefore, what we'll see is that the moment this particular molecule is attached, its T1, T2 is drastically changing. Its dynamics is changing. So anywhere you are expecting that you have a change in dynamics. Earlier it was slow, then it becomes fast. Earlier it was fast, then it becomes slow. Whenever you have such a particular thing, then the T1, T2 is pretty handful. Also, even in protein molecules, how the T1 and T2 are very handy. Suppose the protein molecule is earlier having something like, you have the molecule is something like this. Protein molecule is often like this. So you have a core which is basically very tightly done, and then you have a tail like this. Suppose this is unstructured part of the molecule. So this, what happens that this protons from here will have a drastically different T1, T2 from the protons that is coming from this particular tail, because this tail is basically having a lot of fluctuation like this, right? So the environment is changing. It is not only rotation, but the environment is changing much faster with respect to the protons which are in the structured one. So therefore, if a particular molecule, a protein molecule, is going from a structured to unstructured way, right? Or maybe it has some structured part and some unstructured part. all these things can be studied using relaxation experiments. So the relaxation is extremely important for drug design, for structure, unstructured versus structured part, to identify them. Then to study protein folding, because as the protein is unfolded, when it is completely native, basically unfolded situation, from there it is going into the folded situation, correct? The relaxation changes drastically because the environment changes, the tau-c changes. Imagine you have a long thread, and this long thread, if you just take any normal long thread made of maybe steel wool long thread, it rotates or goes through a water much slower. Now you just make it a small ball out of it, and it moves so same mass, but it moves so rapid just because of the shape. So therefore, when you have a protein molecule which is unstructured, it is rotating even slower. But when it becomes a structured one, it becomes a globule, like a ball, right? Then it started rotating much faster. So therefore, if a protein has to be started, like for example, for some reason the protein is unfolding or folding, this can be monitored directly by changing, by looking at the change of their T1 and T2. So these are a few cases where T1, T2 can be useful, and these are measured in this way. The measurement techniques are pretty simple. Even today, there is no sophisticated measurement technique. Whatever you have learned today, that's the one. Still, the inversion recovery and CPMG, these are the ones. T1 and T2 measurement is done, nothing. If you have to measure someday, you have to use this experiments only. So, okay, with this, I'll stop this, and then if you have any questions, you can certainly ask me.
Okay, thank you, Professor Ghosh.
Yeah.
Participants, if you have any doubt, you can ask your directly, or you can enter your doubts in the chat box. You can speak out actually, participants.
Professor Ghosh, I am Dr. Vijay Kumar. This T1 and T2 is getting
Yes.
affected by any solvent polarity and concentration?
Solvent polarity and concentration of this concentration
Sample.
definitely no. Concentration definitely no.
Of the sample.
Now, concentration definitely no. What happens is that if your concentration is too low, maybe measurement error can come in. But the processes, correct? This process is a molecular process. Even in the if you have a single molecule, the process is basically the same thing. Not exactly single molecule. This is still bulk property. Yeah, but the thing is that in normal situation, in a liquid state, if you have change in concentration, not much. But if we go from, say, all the way from liquid state to solid state, correct, that kind of a drastic change, then yes, then you can start seeing the effect of change in the T1, T2. But I have not seen, just by doubling the concentration, the T1, T2 has changed much. My experience doesn't say that much. Fine, but then again, you have to say that, well, if you suppose you are going from a normal solution to a super saturated thick solution, then again, because this T1, T2, they are basically dependent on the viscosity. If you are changing the viscosity too much, then it will start happening. But normal concentration, little bit of here and there, I don't think so.
Thank you, Professor. Thank you.
Yeah, but you should not just think that, okay, I'll keep adding solute, and then slowly it is going in a super saturated thick solution. Then it will start turning, because the thing is that as I told, so basically you should never do something which actually changes this tau-c, the rotational correlation time. If that changes, T1, T2 changes drastically. So as long as you are confident that you are not changing tau-c much, by changing, suppose you have half a molar solution to 1 molar, tau-c doesn't change much. But if you just make it super saturated, then the tau-c will start affecting. Then T1, T2 will definitely be changing. Yeah, that's what I mean.
Thank you.
Yeah.
Anyone else? Other participants, any doubt or any clarification needed? You can write in the chat box. If not, then I will suggest any doubt you find, you can directly write to Professor Ghosh. He will be happy to answer your questions through email. So his email ID has been shared with all of you. Okay. So please write to him if there is any doubt. Okay, then we can, maybe you can stop it here, Professor Ghosh.
Yeah, I think I forgot to send you the slides of last class, correct? Did I send you the whiteboard for the last class?
Professor Ghosh, I think there is a small post query.
Ah.
That is one participant is asking, if you change the solvent, does it affect the relaxation?
Again, as I told you, this relaxation is a property of dynamics of this molecules, right? So the thing is that if this particular new solvent has a drastically different viscosity than the old one, then you might see that there is a difference. So for example, you go from say CdCl3 to benzene, something like this. I'm not a chemist. A chemist might tell better. I know the physics part, but if the viscosity is changing too much by changing this particular this thing, then this T1T2 will be changing. Also, sometimes what happens, it might look like that it is the effect of solvent. Suppose a particular association was happening between the host and the guest in a particular pH, and then you change the pH, and that particular guest host combination is not happening anymore because of pH for a different reason. But that will be reflected into a change T1 T2 because that guest host combination is not happening. But it might look like that I change my pH and then my T1 T2 is changing. But as far as what I'm trying to emphasize in this question as well as the last question as well, that the T1 T2 is basically dynamics of the molecule, how this molecule is rotating with respect to the B1. If you go deeper into this theory, you will understand that how this particular molecule is rotating, how uniformly, how fast it is rotating in the solution. The T1 T2 depends on that solely. That is why when you are going to the solid state one, when you are restricting it to rotate, then that drastically it will change. Or maybe if you use some kind of say liquid crystals have this long molecules, and then a small molecule can get trapped inside the bunch of liquid crystal, then also T1 T2 you will see that is changing. But everywhere it is changing because you are changing the dynamics. Not any other chemical reaction or nothing. You are changing the dynamics. That is that you need to think about all the time.
Okay, I think happy. It was Sunanda. Sunanda, are you happy?
Yes, sir. Thank you.
Thank you very much. Okay, sir. And you wanted to say something, Professor Ghosh?
No, I just wanted to
Share
say that
it.
whether I have shared my whiteboard in the last slide. I think I forgot.
Sure.
So I'll do both of them.
No, you are recording, no? You are recording, but whiteboard, I think you shared the third one. Fourth one also you shared, I suppose, no? Huh? Okay, I'll confirm it, sir.
Okay, yeah, sure.
Okay, then in that case you can share both the.
Sure.
It
Okay,
is
thank
not
you very
there, sir. Fourth one, it is not there in the website.
It is not shared. Okay.
Okay, yeah, I thought so. Yeah, okay, fine. I'll do that.
Okay, please do share the fourth and fifth one.
Yeah.
Okay. Okay, then thank you very much, sir.
Yeah, thank you. Yeah.
Thank you.